Nobody saw this coming. Not the fans, not the skeptics, not even the engineers watching the test data. Elon Musk had just dropped a revelation that turned excitement into concern and admiration into urgency. The Raptor 3 engine, hailed as a next-generation masterpiece, wasn't just pushing the boundaries of propulsion, it was dancing dangerously close to disaster. And the reason? A flaw so razor-thin in margin that it sounded almost fictional. If the startup sequence missed its precise timing by mere milliseconds, the entire engine could violently self-destruct. No leaks. No warnings. Just instant detonation. It's not just a design quirk, it's the dark side of innovation. The moment Musk confirmed it publicly on X, the spaceflight community froze. Everyone had been marveling at the power of the Raptor 3, 280 metric tons of thrust at sea level, over 308 tons in the vacuum of space, all coming from a sleek, radically simplified design. But now they were staring down the reality: the price of perfection might be catastrophic failure. And yet, as always with SpaceX, this wasn't the end of the story. It was just the beginning of another engineering gauntlet, one that would demand the sharpest minds and boldest moves the company had ever attempted. Let's rewind. Back in August 2024, SpaceX stunned the aerospace world when they quietly revealed Raptor 3. No flashy event. No Elon Musk press conference. Just a set of jaw-dropping photos posted online. The engine didn't look real. It looked like science fiction, a shimmering metallic core, stripped of the cluttered piping and shielding that made Raptor 2 look more like a steampunk experiment than a Mars-ready engine. Industry veterans were in disbelief. Some assumed it was a prototype shell, lacking critical components like the thrust vector control systems or fluid management hardware. It was too minimal, too clean. Nobody believed it was flight-ready. Among the doubters was ULA CEO Tory Bruno, who took to Twitter with a politely sarcastic congratulation. So, there is no need to exaggerate this by showing a partially assembled engine without controllers, fluid management, or TVC systems, he wrote, implying that SpaceX was trying to hype a work in progress as a finished marvel. 4 days later, Gwynne Shotwell, SpaceX's iron-fisted COO, fired back. "Works pretty good for a partially assembled engine," she posted, along with a stunning image of Raptor 3 roaring to life on a test stand, its exhaust burning a brilliant, icy blue flame. Same clean look. Same minimal build. Fully operational. Fully terrifying in its power. That post ended the argument. Raptor 3 was real. It worked. And it was pushing boundaries in ways most people didn't even understand yet. But it also came with a steep catch. A level of complexity hidden beneath its sleek exterior that could make or break the Starship program. Elon's post, the one that triggered this entire debate, revealed the core issue: startup timing. "Very complex startup sequence," he wrote. "Insane timing precision is needed to avoid blowing up the engine." This wasn't hyperbole. It was a technical red alert. So, what makes Raptor 3 so sensitive? Why is ignition such a narrow tightrope walk? The answer lies in the engine's DNA. Unlike traditional rocket engines, which often sacrifice efficiency for reliability, Raptor uses what's known as a full-flow staged combustion cycle. It's the holy grail of rocket engine design: highly efficient, incredibly powerful, and unforgiving. Raptor is the first engine of this kind to ever fly. It uses cryogenic liquid methane and liquid oxygen as propellants, and every drop of them is pushed to its limits before ignition. Let's break that down. Inside Raptor 3 there are 2 turbo pumps, one for the methane, one for the oxygen. These pumps don't just feed the fuel to the engine. They are driven by their own pre-burners, which partially ignite the fuel to create hot, high-pressure gases. These gases spin the turbines that power the turbo pumps, which in turn feed even more fuel and oxidizer into the combustion chamber. But here's the twist. Unlike other engines that dump the leftover gases, Raptor burns all of it. Nothing is wasted. That's what makes it full flow. But it also makes timing everything. Every component has to light up, spin up, and sync up in precisely the right order. And that's the problem. The startup sequence has to happen in a perfectly timed choreography. Just a few milliseconds of delay in one pre-burner, a slight mismatch in fuel flow, or a surge of pressure in the wrong line, and the engine could fail catastrophically. Unlike engines that tolerate minor fluctuations, Raptor doesn't forgive. It doesn't adapt. It either works perfectly or explodes. The process begins with engine chill, where cold propellants are allowed to flow through internal cooling channels. This is essential to prevent the cryogenic fuels from flash boiling when they hit hot metal. After chilling comes spin up, where the turbopumps are brought to high speeds using helium or ignited pre-burner gases. And then, within the blink of an eye, the pre-burners must ignite. The turbines must reach full RPM. The main combustion chamber must accept the full flow of mixed propellants and ignite in a clean, stable burn, all without surging or hesitating. To make matters more extreme, Raptor 3 isn't just a fancier Raptor 2. It pushes the combustion chamber pressure higher than ever before. It routes formerly external pipes inside the engine shell to reduce drag and complexity, creating a compact design that leaves almost no room for error. Protective insulation and redundant shielding are gone. Everything is tuned to the razor's edge. The result is a machine that must ignite perfectly or not at all. This is where the paradox comes in. The very things that make Raptor 3 so revolutionary, its power, its efficiency, its compact design, are the same things that make it hard to control. SpaceX isn't just launching a rocket anymore. They're launching a high-speed chain reaction, a cascade of events that must unfold with robotic precision under extreme conditions. And the startup sequence is the critical domino. If it falls wrong, the entire launch fails before the vehicle even lifts off. So how is SpaceX planning to overcome this? They're doing what they've always done: test, iterate, explode, and improve. According to internal leaks and public test stand footage, SpaceX has already been running dozens of static fires at their development facility in McGregor, Texas. These aren't just practice runs, they're data gold mines. Each test captures thousands of parameters in real time: ignition timing, pressure spikes, fuel mixture ratios, turbine ramp-up curves, pre-burner ignition lags, and more. And SpaceX is feeding that data into their machine learning systems, training algorithms to detect anomalies and suggest improvements. On top of that, engineers are working on refining the startup controller software, making it faster, smarter, and more responsive. The current system uses microsecond-level control loops, but for Raptor 3 that's not fast enough. They're now experimenting with FPGA-based real-time processors that can react at nanosecond speeds, adjusting valves, spinning turbines, and managing pressures in real time. It's rocket science meeting cutting-edge AI. And it might just work. There's also been talk of a hardware change, adding redundant sensors to monitor the spin rate of turbines, pressure buildup in pre-burners, and flow rates through the fuel lines. These sensors could give the computer just enough early warning to abort a bad ignition attempt before it goes critical. In the past, aborting an ignition meant scrubbing a launch. But with Raptor 3, aborting at the right moment could mean saving a $2 billion Starship vehicle from exploding on the pad. But even with these fixes, the truth remains: Raptor 3 is not a plug-and-play engine. It's a volatile, high-performance machine that demands respect. SpaceX knows this, and they're betting that their rapid prototyping model, fail fast, fix faster, will help them tame this fire-breathing beast before Starship's first crewed missions begin. And yet, there's something poetic about this struggle. The same engine that could one day send humans to Mars is, right now, just trying to light without blowing itself apart. It's the ultimate metaphor for exploration: dangerous, complex, and completely worth it. Nobody saw this coming. Just when everyone thought the Raptor 3 engine had broken through the ceiling of rocket engineering, Elon Musk casually dropped a revelation that left the entire spaceflight community stunned. It's the kind of twist that only SpaceX could deliver: unexpected, disruptive, and strangely poetic. The Raptor 3, this marvel of modern propulsion, hides a ticking time bomb behind its sleek design. Because if its startup timing is off by just a few milliseconds, the entire engine can violently tear itself apart. Yes, that's right. Despite its polished look and monstrous power, Raptor 3 harbors a delicate secret. And SpaceX has no choice but to wrestle with this dragon before Starship can roar into orbit again. It all started in August 2024 when SpaceX unveiled Raptor 3, and the internet practically exploded. For those following the journey of reusable launch systems and deep space exploration, it was a monumental moment. At first glance, Raptor 3 looked like something out of science fiction. The usual maze of piping, the exposed cable work, the industrial messiness that defines most rocket engines, it was all gone. In its place stood a design that was almost surgical in its simplicity. Every component tucked away. Every curve smooth and precise. And yet, that wasn't even the most shocking part. The numbers, those cold, unforgiving facts, were even more mind-blowing. This engine could push 280 tons of thrust at sea level and more than 308 tons in vacuum. That's a staggering 22% jump over Raptor 2. And remember, Raptor 2 was already considered one of the most advanced engines ever made. So how was this possible? Many in the community were skeptical. Some thought the image SpaceX posted was a prototype or maybe an unfinished unit. It looked too clean, too minimal. Surely something was missing. Industry heavyweights even took public shots at it. One tweet from ULA CEO Tony Bruno went semi-viral. He congratulated SpaceX but added a sarcastic jab, suggesting they were only showing off a partially assembled engine without fluid control systems or actuators, comparing it unfairly to complete engines built by other companies. That jab didn't sit well with Gwynne Shotwell, SpaceX's iron-willed COO. Just 4 days later she fired back, not with more words but with hard proof. She posted a video of that same minimalistic engine roaring to life on the test stand. That impossibly clean-looking engine wasn't incomplete. It was the final product, and it worked beautifully, breathing a fierce blue flame into the Texas sky. Her caption? Works pretty good for a partially assembled engine. With that, any remaining doubt was incinerated, much like the methane and liquid oxygen that fed Raptor's power. But now, months later, we're learning that not everything was as perfect as it seemed. Beneath the sleek casing and the impressive test firings lies an unsettling truth. Elon Musk himself opened the lid on it during a conversation on X, his social platform. When asked about Raptor 3's ignition system, he responded bluntly, "Very complex startup sequence, insane timing precision is needed to avoid blowing up the engine." It wasn't just a technical comment, it was a red flag. Because if there's one thing rocket engineers fear more than failure, it's unpredictability. And when a rocket engine can self-destruct from being a few milliseconds out of sync, you've got a problem that's as dangerous as it is difficult. To understand why this is such a big deal, you have to grasp what kind of engine Raptor really is. It's not just another iteration of chemical propulsion, it's a whole different species. The reason SpaceX designed it the way they did comes down to one word: Mars. To build a colony on the red planet, you need a rocket that's not just powerful, but also efficient and capable of refueling itself using resources found on Mars. That's why Raptor doesn't run on traditional RP-1 kerosene. It uses liquid methane and liquid oxygen, both of which can be synthesized on Mars via the Sabatier process. But that choice comes at a price. It demands a much more complicated engine cycle. Unlike engines like the Merlin, which use simpler open-cycle designs, Raptor 3 runs on a full-flow staged combustion system. That means both the oxidizer and the fuel are fully gasified and burned in separate pre-burners before entering the combustion chamber. There are no exhaust gases wasted out the side. Every bit of chemical energy is squeezed out of the propellants, delivering maximum thrust and efficiency. It's genius, and terrifyingly difficult to master. That's why Raptor needs 2 separate turbopumps, one for the methane and one for the liquid oxygen, each powered by its own dedicated pre-burner. One burns oxygen-rich gas, the other fuel-rich. These 2 streams then converge in the main chamber, creating a violent and tightly regulated explosion that produces thrust. But here's where it gets tricky. Starting this process isn't as simple as flipping a switch. The timing has to be absolutely perfect. Every valve, every turbine, every pressure differential has to be synchronized down to the millisecond. If even one part is out of step, the result is not just a failed ignition, it could be a catastrophic engine explosion. The first phase of engine start is called the chill down. SpaceX allows a small amount of cryogenic liquid, methane and oxygen, to flow through internal channels that snake around the combustion chamber and nozzle. These regenerative cooling pads are essential. They don't just protect the engine from overheating, they prepare it. Because if those icy fluids suddenly hit hot metal, they'll instantly flash into vapor, creating dangerous bubbles and pressure spikes that could damage the engine or cause an unstable startup. So, everything must be brought down to cryogenic temperatures in a smooth, controlled flow. Once chilled, the next step is the turbopump spin-up. Using high-pressure helium or stored nitrogen gas, SpaceX forces both turbopumps to begin spinning before ignition. This part is nerve-wracking because both sides of the engine, the oxidizer and the fuel, must reach operational speed in lockstep. If one spins faster or slower than the other, you get imbalance. And imbalance means combustion instability. And combustion instability in a closed-cycle engine like this? That's how you lose hardware. Or worse, a full launch vehicle. The final step is ignition itself. The pre-burners light up first, using a carefully measured spark or pyrotechnic igniter to kick off the combustion. These generate the hot gases that spin the turbines. Only then does the main combustion chamber receive the full flow of fuel and oxidizer, and the real fire begins. From zero to full power, this entire sequence unfolds in just a few seconds. But within that time frame, there are hundreds of micro-events occurring at once. And the margin for error is thinner than a strand of hair. A delay of even 1/10 of a second in any subsystem can lead to oscillations, pressure surges, or incomplete combustion. which in Raptor's case could end in total failure. This is the challenge that Elon Musk was warning about. The beauty of Raptor 3, its clean design, its compact systems, its raw power, is also its Achilles heel. Because the tighter you build a system, the less tolerance it has for errors. And in rocket science, even small errors are unforgiving. But this is the price of innovation. SpaceX isn't just trying to make another launch vehicle. They're building a ship that can leave Earth, refuel on another planet, and return. That means pushing technology to its limits, sometimes beyond them. Still, SpaceX isn't backing down. They never do. Engineers are already deep into refining the startup sequence, improving synchronization between subsystems, and testing new algorithms that can manage the ignition process in real time. It's a race against physics, but SpaceX has proven time and time again that it thrives on solving impossible problems. Whether it was landing rockets on barges, building stainless steel rockets in the open air, or turning empty deserts into launch pads, they've made the impossible look routine. So, while the flaw in Raptor 3 might sound like a crisis, it's more like a rite of passage. Every great engine has its growing pains. And every great mission needs an engine that's been tested not just in simulation, but through